Okay, now we're extending what we did in class a little bit. We got the equation here, the condition for an object to be in circular orbit around a planet is that this centripetal acceleration or centripetal force equal the gravitational force. So we repeat that equation up here and mention that we want to solve this for V, as we mentioned at the end of the last clip. So solving this for V, first of all, you divide through by M2, it goes away, and you multiply both sides by R. Well, let's let's do it in a couple of steps just to be sure. And you should have already stopped and solved this. I didn't tell you to, but it should be obvious that that's something you're going to want to do. Okay, well, we divide the M2 out, and there we have it. We're trying to solve for V. We've already got V here. All we need to do is multiply by R, and then we're going to need to take a square root. So we're going to get V squared equals G M1 over just R, so that V equals the square root of G M1 over R. So a very simple solution. This is the velocity of a satellite in orbit around a planet of mass M1 at a distance R from the center. So this is the velocity of satellite in a circular orbit of radius R about a planet of mass M. So there's your formula. Notice that the mass of the satellite M2 doesn't appear here. Now this does assume that M2 is much, much less than M1. If M2 is closer to M1, then we have to change our R a little bit to accommodate the fact that the orbit is about the center of mass of the two objects, the planet and the satellite. So if this is the moon and the planet, your R would actually be the distance from the center of mass, and the moon and the planet would both orbit that center of mass. The moon with the Earth orbits about a point that's slightly inside the Earth's surface, but it's not the center of the Earth in this case. But for a small satellite, communication satellite, anything we could send up, we can't send up a moon-sized object, obviously. This model is going to work. Your center mass is effectively just the center of the Earth for the Earth and a small satellite. One more quick question regarding the motion of this satellite. What's its kinetic energy? You should ponder that. You should write that down. Write down the expression. Get it before you see me do it. I'll come over here. Okay, kinetic energy is going to be 1/2 m2v squared. That's going to be 1/2 m2 times the square root of Gm over R. Getting too many lines up here. And that comes out. And we didn't use big M. I often use big M for the planet, and I kind of slipped and did that there, but that's M1. So we're going to get what? 1/2 G M1 M2 over R. Now that's kind of an important thing, and it's not easy, it's not difficult to derive. If you have a satellite in circular orbit about a planet, you're going to have the two masses. You're going to get the gravitational force. You're going to get the expression for the centripetal force. You're going to set those equal. You're going to get V as a function of the mass and the radius of the planet, and of course the universal gravitational constant. And then you can do 1/2 m2v squared, the kinetic energy of the satellite. So you ought to be aware at this point that those calculations can come about in a fairly straightforward manner.